Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last few lectures of ECE2026, Introduction to Signal Processing, we've looked at discrete time Fourier transforms. In this lecture, we'll start looking at discrete Fourier transforms. This is extremely confusing nomenclature. The DFT and the DTFT are related, but they are different things. And it's particularly confusing because the discrete time Fourier transform and the discrete Fourier transform that doesn't have the word time in the name, they are both transforms of discrete time signals, even though the DFT doesn't have the word time in the name. In the second introductory lecture in this video series, I mentioned some applications of the discrete Fourier transform, such as radio astronomy, magnetic resonance imaging, and radar. Here we have the DFT on the left, and on the right we have the associated inverse transform. Now, having the 1 over n here is a convention. You could create a transform pair by putting the 1 over n here, or I've also seen cases where people put a 1 over square root of n here and a 1 over square root of n here. Those are just different variations. We're going to stick with this version. Unlike the DTFT, which was a function of a continuous variable omega hat, the discrete Fourier transform is a function of an integer variable k, so we're going to use brackets here instead of parentheses. It's basically a transform that takes us from a series of capital N numbers to another series of capital N numbers. Now, there's different ways of interpreting it. If you think about x of n as being a signal that has a certain length, capital N, and is 0 outside of that, then you can interpret the DFT as being a sampled version of the associated discrete time Fourier transform of that finite length signal x of n. So in that interpretation, when you use this inverse discrete Fourier transform formula, you only apply it for little n between 0 and capital N minus 1, and for the little n's outside of that, you assume that's 0. Because we'll see later, if you just brute force plug in numbers for n here outside of the range of little n equals 0 to n minus 1, the resulting sequence here actually replicates. We'll talk about that more in a future lecture when we talk about discrete time Fourier series. Recall that we saw that sampling in the time domain corresponds to replication in the frequency domain. Here we'll see that sampling in the frequency domain corresponds to replication in the time domain. So far we've looked at the DTFTs of signals defined by simple mathematical formulas. The DFT gives us something we can do on our computer and compute samples of the DTFT of arbitrary finite length signals that we measure. Recall our original discrete time Fourier transform formula. Now, that formula applied to infinitely long signals. Now let's suppose that our signal is 0 outside this range of little n equals 0 to capital N minus 1. And let's evaluate our discrete time Fourier transform at specific frequencies, namely a set of samples that are 2 pi over capital N apart. Now, if I take this omega hat sub k and plug it in here, we see that that's equivalent to the discrete Fourier transform that I showed you on the previous slide. So the DFT is very convenient because it gives us samples of a discrete time Fourier transform that we can plot. One thing to remember is that big X in general is complex valued. Here we're imagining a case where big X happens to be real valued. When we make plots, we'll often plot the magnitude and the angle separately, or sometimes we'll just plot and look at the magnitude alone. The discrete Fourier transform is periodic with period capital N. That relates to the original discrete time Fourier transform being periodic with period 2 pi. And then we have our associated inverse transform. Now, I've referred to signals of length n and said, let's take an n-point discrete Fourier transform. Let's modify our nomenclature a bit and talk about signals of length L. We might want to take a discrete Fourier transform that is an endpoint transform where n is bigger than L. And the way we do that is we just add a bunch of zeros at the end. We'll talk about the effects of this zero padding later. Recall that the DFT must be periodic with period capital N because the underlying DTFT is periodic. Now, remember that the discrete time Fourier transform had conjugate symmetry in the case of real-valued signals little x. The DFT inherits that conjugate symmetry. Notice that we can combine the conjugate symmetry with the periodicity and write big X, capital N minus K, is equal to the complex conjugate of capital XK. So, for instance, if capital N was 32, X of 31 would equal X complex conjugate of 1, X of 30 equals X complex conjugate of 2, and so on. And again, this conjugate symmetry only holds for little x signals that are real valued. Let's imagine plotting the values of a discrete Fourier transform. We're using the heights to indicate magnitude and aren't explicitly plotting the phases. Along the top axis, we're plotting the DFT index k. The various lines correspond to points on the discrete time Fourier transform along this omega hat axis. The DFT is periodic, so you'll see a copy of this structure up here, and you'll see a copy of it down here. And assuming little x is real valued, it also has this conjugate symmetry. Now, when we talked about discrete time Fourier transforms and frequency responses, we usually focused on this region between minus pi and pi. Here, we're usually focusing on the k between 0 and capital N minus 1, inclusive. That would correspond to a region in the omega hat land between 0 and 2 pi. We make this slight modification of where we're looking because we're usually computing this DFT on a computer, and it's very natural in a programming language like C to have data arrays that start with an index of 0. The essence of a DFT is a transformation from a vector of n numbers to another vector of n numbers, and that transformation is linear. So it's possible to organize it as a matrix multiplication. In MATLAB, you can type DFT MTXN, and that will give you an n by n matrix that you could multiply by a vector little x to get your vector big X. But a brute force version of that requires n squared computations. Fortunately, we have an algorithm called the fast Fourier transform for computing the discrete Fourier transform that was published in 1965 by James Cooley and John Tukey, although it looks like it was discovered over 100 years earlier by Gauss. The FFT reduces the computational complexity from order n squared to order n log n. In the next lecture, we'll look at a particular example. We'll detail the calculation of a few brute force DFT calculations. We're not really going to talk about the details of the FFT in this class.